Hey, what's going on, man? Yo, what's up? All right. Anybody interested in understand? I'm just gonna tell a story since some people in here. All right. So here's our brain. Here's the limbic core of it. Here's our cerebellum, and this is our cerebral cortex. And here's the octopus. Now, technically, our planet is actually a gastropod. It's a mollusk in nature. It's a crustacean. It's an invertebrate, or it's a pod of gas. It has a mantle. It has a crust. It also forms cave pearls. Okay, our planet forms calcium carbonate pearls in caves using the same method that pearls are actually formed in oysters and such. So our planet is literally, by nature, it's an invertebrate mollusk. Okay, so technically the octopi, pie, like our cerebral cortex, we have 8 lobes of our brain, basically square area twice. It's this right here. Now, let's see. Of course, it's got the gyroscopic thing here. Get in here. Early evolution. Alright, so... Hey, look, it's our planet. Basically, it's a sun. It's got a convection zone here, kind of like an orange. It's got the same convection mimicry. Just like the Earth here in the mantle convection zone. Alright, here's the pore bearer. This is the sponge. This is what's going to eventually become our flesh, because we have pores in our skin, and our skin has to breathe. You know, if you get tarred and feathered, basically your skin gets suffocated, so because it has to breathe. Now, these guys breathe similar to how our skin breathes, except for they have to use water. But nonetheless, this is a precursor to our flesh, the sponge, the pore bearers. See, in evolution, like time, God, nature, whatever anybody wants to call it, is like a scientist. Whatever it is, it's working this stuff out. All of the organs in our bodies are basically filters. You know, our kidneys filter our blood, our lungs filter the air, our stomach filters out nutrients, our brain filters out information. Now, this is what's wild. This is actually the brain of an octopus, which it has no actual brain, but there's only one area in its head, and then it tentacles out into 8 other brains. So it has 9 total. But this is the inside here, and doesn't that look like our kidneys or our lungs or something? I mean, it just looks wild. Of course, this looks like our pelvis, but this is a squid's brain. Here's some coral. And the coral is going to be our bone. So it's the calcium carbonate. It's the hard. You know, it's like evolution's going to take everything. It's going to make hard on the inside like us and soft on the outside. And then it's going to make soft on the inside and hard on the outside, you know, which have exoskeletons. So it's the endoskeletons and exoskeletons, but it's working out all the chemical synthesis in the ocean. You never seen RoboCop? Remember how they cut Kane's brain out and they put it in that big vat with all the bubbles in it? It's in that liquid. Imagine something like that. You know, like nature is a scientist and it's working out all the organs in the ocean, you know. See, here's some coral, which it's weird, technically all this stuff is related to fungus. You know, fungus is known to manipulate its environment to make it more conducive to its own survival. And technically, that's us. I mean, any animal that has a will or an intelligence, the oldest form of will and intelligence and chemical synthesis and actually having, you know, a will to survive and altering the environment is actually the fungus. You know, this is liverwort. Look how close it looks like to a mushroom or a fungus. Technically, it uses spores just like a fungus does. But this is early evolution of the spore because it hasn't evolved into a seed yet. But it's going to. It's going to evolve into a seed later on. Now, we're 50% related to fungus, and we're 50% related to trees. This right here looks like a mushroom. but it's a cnidarian. It's a jellyfish. You know, it looks like the trunk right here, which is our torso or trunk, but this could be our thinking cap, you know, like our thinking cap, the fruit body. And these tentacle out into our body, which is basically our veins, you know, the mycelial network that stretches through our body. You see? And it gets nutrients from our body too. Because our body's like a little Earth. It's a little mini Earth that's got all the same constituents as the planet. See? And here's the thinking cap. You know, here's our torso or the trunk here. And then there's the mycelial network. I don't know what it was telling me to do. Anyway. So, and here's our brain and our network there. See, it's like a mycelial network. That's our thinking cap, and it looks just like a cnidarian, like a jellyfish in a way. It's put all the stuff together, you know. And this is analogous to like a Venus flytrap, because at some point, the earliest things are photosynthetic organisms and fungi, and of course it diverged, you know, from spore and it evolved into seed. But this is going to be like our digestive system. I mean, this is our mouth. This would be like our throat, and down here would be our guts. That's where we absorb the nutrients from whatever we digest up here. And digestion begins in the mouth. You know, our saliva is like a corrosive enzyme. It's similar to how a Venus flytrap is. You know, it emits, it secretes an enzyme in its mouth to be able to digest the bugs. You know, so that's an early stage of our evolution. Here's another carnivorous plant. Now, these carnivorous plants are going to evolve, obviously, from fungi because technically fungi is carnivorous. All right, here we're going to start getting to the octopus and the Catholic Church. You know how they got their tentacles and everything. You know, these are like the tentacles, and this would be like the crown chakra. See, the Earth, since our Earth is literally a mollusk in nature, this is its version of itself. You know, we're like the universe. We're like the universe version of itself, and this is Earth's version of itself. That's why the octopi is such a unique animal. It's because once the spore came into the planet and it can metabolize, so basically the mollusk. Nobody gives a fuck about evolution, do they? Nobody gives my shit. I don't even know what the hell to explain, man. Basically just waste my fucking time. Oh yeah, that's a singularity. Just saying. Anyway. Basically the octopus is like Earth's version of itself. Since the universe, we're like the universe's version of itself, then the octopus is an invertebrate mollusk. Since our planet is a mollusk in nature, it's a crustacean, it's an invertebrate, it's a gastropod, it's got a mantle, it's got a crust, forms cave pearls the same way. I mean, our planet's a giant mollusk. Anyway, so you have your octopi, you have your 4y plus 4x, gives you z. Okay, so that's your two axes here, your y-axis and your x-axis, octopi. This is good. It's going to be our brain. This is a precursor to our brain. The octopus is literally our brain. All right, so you have your 4x axis flat, then the diamond would be the 4y axis. So you have two God's eyes. You have a left eye and a right eye, which are both God's eye. You know, we can see. You know, we can comprehend the nature of the universe with our eyes, and our brain does emit light. We do emit light from our eyes, because if you do not emit light, you can't receive light, you know, because your brain's not alive. So if the brain's not alive, it's not emitting any light, and the lenses in your eyes can't receive light because, you know, you're not alive. So our brains do emit light, and it has the quantum entanglement, or not the quantum entanglement, but when it comes to waves and particles and observation, this ties into that factor. It ties into the factor that our eyes do emit light. So the observation, paradox, observer's paradox, is technically, it's not really a paradox. It's just the way scientists keep looking at it. You can't look at it like, our brain doesn't emit light. I mean, seriously? I mean, I know our brain emits light. It has to, because it's alive, So if we're seeing something like a camera, how do you take pictures with a camera if it doesn't have its own little system in it, A regular camera that doesn't have a battery has a chemical process in it. And that's a type of energy. That's an energy process. And it's using the light to capture that. So, the light is, obviously everybody knows the light's everything. And these are tunicates. It looks like a heart. But it's nature working things out. These are all animals in the ocean that are going to be our organs eventually. It's putting all this stuff together. Once it works it out, it's going to put it all together, and all kinds of forms of animals are going to evolve. It's a heart, Of course, this would be like our crown. That's our brain. The cap of mushroom. Ultimately, over time, the eel is going to evolve. Or agnathan. Technically, it's agnathan. They have no bottom jaw yet. They have no spine. They're only an elongated animal with a little bit of skull. So it's going to be early in evolution. Of course, the leech, he doesn't have any teeth yet. The bloodsuckers have to evolve. The bloodsuckers have to evolve to kind of mediate the animals that eat the grass. Because if too many animals are eating all the grass up and the vegetation, then that can cause an extinction too. But grass itself, plants themselves, actually even cause an extinction around 1 billion years ago. And Earth, every time an extinction happens, it learns. Like the plants cause an extinction, and it's like, all right, I need to evolve some animals that'll eat these plants. And then if those animals cause an extinction, it's like, all right, I need to evolve an animal that'll suck the blood from those animals, So this is how it forms the food chain over a slow period, So it learns every time an extinction happens. This is a lamprey. This is agnatha. These are eel-like animals, and eventually will evolve into eel. There's the hagfish. Here's a moray eel. Very unique jaw. They got pharyngeal jaws. Pharyngeal jaws are similar to like the animals on Tremors. You ever seen the movie Tremors? They have basically little snake mouths inside them. Or you can consider it like the alien, the xenomorphs. They got a little mouth inside their big mouth. That's how moray eels are. And here's a shark. Actually, they got a similar kind of effect. They don't have bones. Only their teeth is technically bone. The rest of their body's cartilage, but they do have a skeleton. It's a cartilage skeleton. It's like, imagine how you take an egg and you put it in some vinegar and it pickles it. Sucks all the calcium out. That's basically what's up with cartilaginous animals. They got a pickled skeleton, essentially. And he's got like a pharyngeal jaw, too. And that's one reason that the sharks have such a strong bite. Here's a frilled shark, which is eel-like. Early stages. Water cephalian. This is an amphibian. This is a eel-like amphibian too, And eventually this guy's going to sprout little limb buds. Here's a snake. Snake splits right here. That way it can swallow its food. The cephalian's jaw is no different. It swallows its food whole too. But it's got a dual-jointed jaw. So their jaws are actually rather unique, like the snakes and other lizards, as a matter of fact. Now, they say that snakes was some lizard, a four-legged lizard, and then just lost its limbs, but it doesn't make sense. You'd think that an elongated, simple structure would evolve first, and the spine would evolve first, obviously, and that's, the eel and fish that are eel, okay? You'd think this would evolve first. So you'd rationally wrap your mind around the fact that perhaps reptiles that are elongated without limbs evolved from an amphibian that's elongated without limbs. You know what I mean? And this is even a mutation right here. This is a snake, but it's got vestigial legs. It's a leg mutation. It's like it's going to evolve them, and it hasn't evolved them yet. But the salamander is a progenitor of all of the tetrapods, the lizards. Now let's see. So you have your cephalian, which is elongated. He doesn't have legs, but he will sprout little limb buds and evolve into another type of amphibian that has legs, okay? But he's still going to evolve. He's still going to remain. He's going to be around, you know? So he's going to evolve into a cylindrical type of reptile, while these guys evolve into tetrapodal reptiles. So you have snakes evolving, then you have lizards evolving, and that's why they're so closely related, because they're technically first cousins. And amphibians have really unique DNA, especially the axolotl. Because the axolotls are salamanders, but not all salamanders are axolotls. But they do have one of the largest genomes, besides a fruit fly. But also, they can alter themselves. Like, you ever heard of the Peter Pan syndrome? You know, these things, like, they don't want to grow up. You know, they can alter their DNA. They can either remain in a larval kind of stage their whole life and grow to an adult as a child, or they can enable an enzyme in their body as they're going through their metamorphosis the exact same way as a frog can. They can turn themselves into a mole salamander, you know, a large burrowing land salamander. So, you know, these are indicators that these animals, I mean, it's not, oh, this animal does this weird thing. You know, I mean, it's not weird. We need to start applying this stuff I believe, in understanding evolution, because once we understand our polymorphic, you know, our morphism, of course, these guys are in a separate lineage, then we can understand diseases a lot better. I mean, we'll understand how we came to be, you know. And this is, you know, look how long the monitor lizard's necks are, you know. These subtleties, you know, are indicators. Because these animals share traits. And when they say, oh, it's just convergent evolution, just, you know, if it's just this or just that, just this or just that, we're not going to make any sense of it because we're not trying. If they're like, oh, what's just this? Oh, what's just that? Well, take that just this or just that and start looking into it. You know what I'm saying? Take the science to a new frontier. I mean, I swear, we've been hung up. I mean, we just haven't been doing that. I just don't believe we've been doing that. You know, when I watch TikTok and stuff, I see the same old stuff. I hear the same old stuff. You know, I've been hearing the same stuff for 30 years. You know, and nothing's changed other than a bunch of drama. But I'm just saying. So at some point early in evolution, from these eel and these large eel-like fish, a giant fish is going to evolve. And it's anapsid. It's a lobe-finned fish. And it's going to diverge in two ways. It's going to stay in the water and evolve as some amphibious, it's a super amphibian, it's an ichthyosaur. It's not necessarily a reptile. It has a reptile skull because it's in the same spectrum as a reptile, because it's a super amphibian, but it's not quite a synapsid yet. It's not quite a mammal yet. It hasn't evolved into a whale yet, but it's going to over a few 100 million years. And because they're so large, they're going to evolve slower. So the anapsid passes genes to come to the land as anapsid amphibians, and it also passes genes to become a diapsid amphibian that remained in the water. This is our special lineage. This is our own lineage. And this solves the placenta problem in evolution too. Okay, when we get there. When we get there. Okay, but it does. It solves the problem with placentas because no animal that lays an egg is going to mutate to lay an egg that's mutated to hatch an animal that's a placental, okay? Evolution doesn't work like that, and it can't work that way. That just doesn't happen. And that's the placenta problem when it comes to evolution that scientists will not address, and they keep running from. They run from, and I'm not trying to be an ass, I'm just saying. Running from it, man, isn't solving it. If you're a scientist, be a scientist. You know what I'm saying? So over time, these ichthyosaur, see, they're still kind of reptilian-like because they're a reptile-like mammal. Okay, they share all kinds of mammalian traits. They share all the traits with whales and dolphins. You know, they got blubber, they give live birth, they have conical teeth, they fill in the same ecological niches as the orca. They're pack animals. They travel, you know, in a herd. Like they have a hierarchy. You know, well, we don't know. They speculate this. Science speculate. You know, but it's the way that they believe these animals were because they were just like whales, you know? So at this point, like back in the past, under 100 million years ago, around 90, 80 million years ago, after more, you know, extinctions, you got heat waves, you got all kinds of problems going on because the Earth is kind of, you know, it's pretty active. And these animals are going to end up mutating. And that's why the Basilosaurus, now we know Basilosaurus is a whale, but he's reptilian-like. He's got a lot of, proto traits. But that's okay, because it makes perfect sense, because he still hasn't evolved quite to the whale yet, but he's still on his way. All of these Archaeoceti, now the ones on the land, all it indicates, because they found aquatic fossils of whales that are as old as the ones on the land, okay, 49 million years old, it doesn't make sense, okay? There's a hole there. All that indicates is that marine mammals and four-legged mammals existed on Earth at the same time then that they do now. That's all it indicates. It doesn't say, oh, well, this animal evolved from this, or this animal evolved from that. That's like me saying, oh, because this animal, that's like saying, oh, a dog evolved into a human, because it's got 4 legs and I got 2, so a dog had to stand up, But we know we're related to dogs, and I'll get to that too. We're actually we're the 80th percentile, 84 related to dogs, but we're 90th percentile related to cats, and that is pretty explanatory also. Okay, it's not a paradox. Because these scientists aren't using DNA, they're using whole leaf fossil records. And I've just been using the fossil record as a guideline, but I've been just straight up going through DNA. Anal retentive, left and right. I mean, that's all I do, man, is draw diagrams, doing DNA, figuring things out, and the DNA says a different story. I mean, it's not wrong from what the scientists are saying, it's just the exact opposite. The DNA is saying that the whales came out of the water, and as they came out of the water, and from evolving from the water into us, it laid a path of all mammals. The mammal of the ocean evolved into all the mammals on the land. And that's why we share so much DNA in the 90th percentile with dolphin. To be quite honest. It's not unusual either, because that's a baseline of DNA. The older you get with the core, the baseline of the animal, there's going to be a lot of DNA shared. So, they tend to, I don't know why. I don't know why they look at a wholly fossil record before they do DNA. I mean, what's the point in us having DNA evidence and DNA and spending all this money on DNA tests to test mummies that have been dead for 2,000, 3,000 years, DNA testing the genomes, all these animals, and when it comes to evolution, we're not using the DNA, I mean, that's beyond me. I mean, that's. Oh, man. Anyway. Hold on. Let me get to a couple things here. All right, see, the fish has its lineage now. And all their hearts actually going to evolve too. So you got a two-chambered heart, because the fish, he's in the water, two-chambered heart. Comes to the land, as all these amphibians, they got a 3-chambered heart now. They're going to continue to have 3-chambered hearts as long as they're cold-blooded. But the crocodile is the only cold-blooded reptile with a 4-chambered heart, the crocodilian order. So, from these four-legged tetrapods that have 3, some of them are going to remain cold-blooded, and they're going to evolve into a 4-chambered heart, cold-blooded animal. And another version, or another animal, or another ancestor of these 4-legged tetrapods that have 3, they're going to evolve into monotremes, which have 4 chambers, and they're warm-blooded. And these others are going to evolve into ducks, which, birds, they have 4-chambered hearts, they're endothermic, but they don't have a mammary gland yet. See, these guys it's like a predictive evolution, okay? I predict that if birds are around for another 20, 30, 40 million years, that they're going to evolve a superficial mammary gland also. They're going to catch up with these guys. They're going to do the same thing. Because there's a pattern that keeps showing up. There's a consistent pattern. And it's with the mammals and it's with the egg layers. And it's always the same pattern, no matter what you look up. If you look up bite force, if you look up their running speed, if you look up if they have ears or not, I mean, if you look up their fingers, how many fingers they share, all of these factors, if you keep look, even their stomach evolution, you'll see the same pattern keep showing up. It's consistent. Evolution isn't random. It's not nonsense. It's not wild. It's not, a random mutation here and there. It actually knows what it's doing. Oh, I'm just going to throw this out here because this kind of coincides with the alien greys. All right. So, I believe the alien greys actually evolved on this planet. And they are a type of reptilian because at some point, remember, you got your theropods, because frogs are an amphibian. They're hind locomotion, okay? I believe that the frogs, or an ancestor of the frogs that are hind locomotion, are going to evolve into birds, which are hind locomotion too. And you have your 4-legged ones, the amphibian, that are going to evolve into the 4-legged reptiles, and then the 4-legged monotreme, okay? So these cold-blooded animals that are amphibian are going to be cold-blooded reptile, then they're going to become warm-blooded mammal-like, okay? But this is a tetrapod, this is a theropod. If you put both of these together, you get a sauropod, okay? And we know that with dinosaurs, okay? We can observe how their skeletals, like their legs, are positioned under them, kind of like a horse or a cow. But through the same processes that similarly to how we evolved, these guys could evolve. A humanoid in the egg-laying lineage literally can evolve. There's nothing odd about it. This thing could actually evolve. Once I figured out this pattern and stuff, I mean, I was always kind of sketchy on the alien greys. I've kind of believed that they're possible, but I didn't, my theory was as good as anybody else's, you know what I mean? And then I started getting into evolution, and then I ended up figuring out that there's a possibility that a sauropodal, egg-laying humanoid could evolve. Millions of years ago. Because animals that are smaller than us, like such reptiles, birds and such like that, they mutate faster. That's why there's way more species. They evolve faster because they mutate faster. And because a lot of these animals are smaller than us, and there's even these guys are said to be real little guys, the size of children, So it does make sense that these things could evolve. Just throwing that out there. I know it sounds weird, but I'm a weird guy. And there's another thing when it's like evolution. When the conservation of evolution, it's similar to the conservation of energy. Once evolution or energy, once it's got a pattern, it consistently follows that same pattern. And this is like our legs, because we're hind locomotion. And frogs are hind locomotion. They jump, they jump instead of walk, but that's their primary propulsion. And they look a lot like ours. Minus the butt, Because, that used to be a fluke. That actually used to be a fluke. Believe it or not. See, right here, this is a lineage of the reptiles. This is the lineage of the mammals, okay? They have the anapsid, which is a fish, and an anapsid, which is a fish, okay? The diapsid's going to evolve here in our lineage, which is the ichthyosaur. An anapsid is going to evolve up here, which is an amphibian. Then the diapsid's going to evolve, which is a reptile. But this thing has all these, smooth skin and blubber and such like that, traits that would be more mammal. So it's in the reptile spectrum when it comes to a skull, but it's technically a proto-whale, because eventually it's going to evolve into a whale, and it's going to come out as four-legged animals. It's going to transition into four-legged animals. Just like through this 100 million years, they transitioned into theropods and cynodonts, because the same pattern happens. The guys in the water come to the land. I mean, it's as simple as that. The guys in the water come to the land, and it happens every 100 million years. They say it happened 200 million years ago. These animals were coming out as therapsids, or they were still reptile-like, but they were mammalian-like also. But they hadn't made it quite to synapsid form. They were synapsids, but they weren't placentals, because evolution hadn't gotten to that point for us yet. That's going to happen in this 100 million years. So you have 300 million years ago, 200 million years ago, and 100 million years ago. And a lot of our traits came up within the last 100 million years. I mean, obviously, but it's consistent. See, it diverged two ways. You have one family lineage here, you have one family lineage here. We're all four-chamber heart, placental, warm-blooded animals. These guys evolve into warm-blooded animals, but we originated that way. We also originally had a four-chambered heart. We remained in the water and gathered ourselves before we started to step out, this last time. And the brain was the last thing to evolve in the cetaceans. Just like on land, the brain was the last thing to evolve. Hence, the human and the human brain, So the same pattern even evolves whenever it comes to the organs, So even whenever they say, elephants popped up, proboscidae popped up, 65 million years ago, it technically didn't pop up. If it was here then, if there was an extinction right here, and these animals are around, they had to have existed prior to the extinction. They were just in a different kind of form. Their DNA might have been a little bit different. They were a different type of animal, but nonetheless, the DNA was still there. So they didn't technically go extinct. They managed to survive and readapt to a new kind of environment, So it's not that they popped up and nothing technically went extinct, There's a grave, there's a, it's odd whenever we consider like extinction facts. I mean, it's like even scientists agree on it, they kind of, need to go through it and kind of relabel some stuff because it seems a little confusing the way we got it labeled out now. You know what I mean? Like, an extinction. They were extinct, but we have animals of them now. So they couldn't have went extinct because their DNA lived on. You know what I mean? It's like the Neanderthals. Neanderthals didn't technically go extinct. We're related to Neanderthals. We got like 8% of our DNA is Neanderthal, They were just bred out. The mix and match, the higher genome's going to eventually just take over, And just like this, they claim, this evolved into some big whale, but there's not enough cellular energy. There's not enough cellular energy in that. Conservation of energy. You can't get more out than when you put in. But these guys can pass dwarf species. And we see dwarfing mechanisms all the time. We see pygmy whales, pygmy sperm whales, dwarf whales. This dwarfing mechanism is absolutely necessary in evolution. Notice that the big animals, all the big animals, especially when it comes to monitor lizards, there's the Komodo dragon. It's the biggest one. Notice that it's got the same exact skeletons as every other Komodo or every other monitor lizard, no matter if it's a Nile monitor or savannah monitor. All of them have the same skeleton, It's like there's only so many animals, but they vary because, they pass all these dwarf adaptations and they become different species, but they're technically... That's another thing that scientists got misclassified. When it comes to a species like Panthera leo and Panthera tigris, okay? That's a tiger and a lion. They're both of Panthera, but one's tigris and one's leo. That means technically they're of the same species, but just a different ethnic group. And I know it sounds weird to start applying ethnic groups to animals, but that's what we need to do. Because they're like us, and we're like them. We're animals. We can't separate ourselves and make ourselves so much different when we're an animal too. You know what I mean? So I think we're going to have to, kind of accept that. And when it comes to hybridization, the artiodactyls have the best rate of hybridization. That means even if they're in a different family, like deer, the deer and the bovine can actually have a child. It's called a blesbok or a deer cow, But the deer is in Cervidae family. And the cow is in a bovine family, but they can hybridize. Just like the cow, or the tiger and the lion. So that kind of makes them a different ethnic group. You know what I mean? It's weird. It's like even the goat and a sheep, they're obviously about the same animal, but they're in a bovine family, but they say they're of a different species. One's a goat, one's a sheep, but they're not. They're literally not. They're in the same family, and they can hybridize and have a sheep goat. So they're basically the same animal. They're not even a different animal. And these are all spines, because that's what I like to do. I like to make sure myself. I don't, whenever you listen to what scientists, we got all the data. We got all the data we need, okay? But when a scientist gives you the information, and then he tells you what he thinks or theorizes on the information, that can taint your own theory. So it's good to just take into what they're saying as consideration, but go ahead and go through the information yourself and see if you get a different picture, because you might, And that 27 isn't arbitrary. Like, there's 27 discs here, okay, when it comes to the walrus, okay, the CTL. That's the cervical, thoracic, lumbar. Okay, he's got 27. That's 9, 18, 27, the 3 nines. Okay, that's not arbitrary because our lunar orbit is 27 days. The pion is 270 times bigger than an electron. The muon is 207 times bigger than the electron. And if you divide muon by 3, you get 6/9, So the same math applies whenever it comes to astrology, like quantum physics, astrology. It's all the same numbers on different scales. Even when it comes to biology, you'll see the same numbers pop up, like the 27. Even the walrus has 18 teeth, Even the hippopotamus has 36 teeth. So the 18 is 6 times 3, and the 36, is 6 times 6. It's just weird stuff like that. And it's not arbitrary. It really isn't arbitrary. If you follow weird stuff like that, it leads you back to the Greek. And the Greeks knew something. And I'll get to that. I'll get to that too. But this is what I theorize here. This is, let me get to it real quick. Okay, so here's our spine and our pelvis. Okay, here's the bottlenose dolphins. All right, now I isolated which ones, I darkened in which ones are the ones here. Okay, so I started down here, the coccyx. There's 4 down here. I filled in the 4, I filled in our 4, and so on with the lumbar or the thoracolumbar right here. And these right here, I filled them in. Okay, that left me 31 bones in between. We have 31 bones in our legs. We have 31 in this one, we have 31 in this one. We have 27 bones in our hands. 27 times 2 is 54, which is 6 times 9. And that's actually a cube. That's the cube, 6 times 9. And you have 27 sectors in the Rubik's Cube. It's the perfect circle. You know, squaring the circle, perfect circle. That's mankind, that's what happened. It's like this factor right here when it comes to the Vitruvian man. 7, 5, 9, 3, and 12. You add these up, you get 36. You add these up, which is because the Vitruvian man has 2 positions. And one of them is even, looks like Jesus on the cross. Just saying. You add those up, you get 30. You take this 36, you take this 30, and you add them up, you get 66. You know what I mean? It's just weird. You know, it's a code of the universe, and Leonardo da Vinci knew. He knew it too. You know, so like right here, if you take out the animals that we know are extinct, just take the extinct one out and just use the DNA, okay? You clearly see the pattern with the whales evolving into the artiodactyls. And here, this is Odobenocetops. This is the walrus-faced whale, okay? This is a transition in between the walrus and the whale. But nobody hears about Odobenocetops. And the walrus is his own. That's his. He's alone. You know, the walrus is a lone pinniped. There's only 2 species of walrus, and they can hybridize, making them technically only 1 species of walrus because they're just 2 ethnic groups. The dugong. These guys even have tusk. The dugong, they're manatee. They're Sirenians. And if you look at their fingers and their arms, see evolution. Whenever it comes to us, when we diverge from our amphibian and we start evolving, you know how tadpoles, when they grow, they sprout their legs. Their hind legs first, then they'll evolve their front legs, okay? Well, we are a little bit inverted. The manatee evolves, that's like the tadpole's version that has 2 little hind legs. Except for our version, it's the manatee and he has his 2 front limbs evolved, okay? Hasn't gotten to the hind ones yet. That's going to be the pinniped, the walrus. You see? We're inverted from the reptile lineage. Just like they come out of the water as a hind gut fermenter. That means they don't use their stomach to digest like a cow would, which is a ruminant, that we use our intestines. That's a hindgut fermenter. All the reptiles came out as hindgut fermenters. And then when they got to the platypi stage, their stomach is gone. Like in the predictive evolution I was talking about. I predict that we're going to follow a same pattern because inverted from that, we came out of the water as foregut fermenters and over time evolved into hindgut fermenters, okay? I predict, if we follow that same pattern that the reptiles did, that we're going to lose our stomachs. We're not going to need our stomachs. Given a few million years, we're only going to be hindgut. Literally, our stomach is going to be a little vestigial stomach. And we even see that now. People have gastric bypass and they live just fine because we really don't need our stomach. It's good to have. It helps break down. It helps give the extra enzymes. Makes it a little bit easier for your liver and stuff to break down the food and your intestines to absorb. But ultimately, we're going to lose our stomach. It's a theory, but I believe it's going to happen. All right, so these are the types of seal. Okay, this is the pinniped. This is our amphibious version when we started to come to the land. Okay, these guys are true seals. Okay, they're earless. These guys are all going to evolve into the feline species. Okay, these guys right here. These guys here are eared seals. They're going to evolve into the canine species. The walrus is us. This is going to be he's related to artiodactyls. Whenever the extinction happened, the pinnipeds took it hard for some reason. Their species, their number of species is a lot lower than it should be when you do the pattern. It's consistent, but with them, there was a severe drop. They didn't take extinction too well. But I'm glad the walrus survived because we might not be here. But if the survivors didn't die like, they did, there would be an animal that's closely related to hippo that's closely related to the walrus too. And it may be Odobenocetops, because we know the hippo is a water horse. He's amphibious. So he's still got that instinct for the water. Plus he's got ivory tusk. The walrus has ivory tusk. The whale has ivory tusk. And the dugong have ivory tusk. The elk has 2 ivory teeth. And the warthog has 2 ivory tusks. If we trace the ivory, this is one reason why we're actually closer related to a cat. This is why we're in the 90th percentile related to the cat. And we're 80th percentile related to the dog. Okay? Because you have your leopard seal, which is Phasidae. These are going to be the felines. They're earless. Okay? They're going to evolve into hyenas, mongoose, civets. That's a carnivoran lineage. But there's also the other carnivoran lineage, which are the canine. Otaridae. These are the sea lion, eared seals. They're going to evolve into bears, skunks, cynodesmus, raccoons, wolverines, otters. And now, of course, obviously, the whale's tail, after it recedes, it's going to split. The hips get better. You know how there's they say it's a vestigial hip, and it's a remainder from whenever the whale walked on the land? I don't believe that's true. I believe it's a seed hip. It's a proto-hip. It's something that's a little seed that's going to grow into a big pelvis area. And the more these animals come inland in shallower waters, that hip does get better and more advanced, and that tail does recede, and it literally does split into 2 hind limbs. It literally does. Okay, so these were cat traits and such, with the nose and the traits of the cat with earless seals. Yeah, check this out. This is a marine animal. And look, there's our nose. That's literally gonna. It's gonna move to the front of the face. Now look, it's on top of the head. The walrus's is actually on top of his head too. The nostrils on top of the hippo, theirs are positioned to the top. They haven't made it to the front of the face yet. They're still positioned toward the top of the head along the eyes. Okay, now let me get to her. This is, of course, the pinnipeds, the legs and arms. They're just getting better and more human-like. Okay, check this out. All right, this was what I was talking about when it comes to the hybridization, of ethnicity, like the pig. It's Suidae. This is Tayasuidae, which is the Picari, but they can hybridize. There's only one recorded case of a earless seal and an eared seal hybridizing, but ultimately they found a hybrid, so they can actually crossbreed. And when animals are faced with an extinction event, don't think for a second they're just going to think, oh, well, they're not an eared seal like I am. I ain't going to, procreate with them. No, they're going to pass their DNA one way or the other, Animals at those points, extinction events, animals panic. They'll do anything they can to survive, and that's a will to survive, Anyway, here's a pattern. This is the same pattern, but ultimately this is our teeth pattern, okay? So you have your Odontoceti. He's got 36 to 56 teeth. The walrus has 18. The hippo has 36. Now, the okapi, camel, sheep, goats, deer, giraffe, moose, cow, and antelope all have 32 teeth like us. The warthog and the elk, which have ivory, have 34. Okay? Now, since we're in the bovine family, and we're related to antelope, we're actually related to the antelope. And the the kangaroo is actually related to an antelope, believe it or not, because, Procoptodon, it's extinct now, but it's a hooved kangaroo, okay? Because at some point, when we're faced with an extinction, the antelope stood up on their hind legs to reach high foliage. Now, giraffe, their necks had to extend. They evolved long necks to be able to reach high foliage in trees, okay? The antelope, the same constraint that made the giraffe's neck long is what forced our lower region to start evolving, okay? But anyway, I'll get to that. This is 34. They have 30. That's the koala and the kangaroo, okay? He has 2 more, and he has 2 less than us. We're related to both of these guys. We get a lot of our traits from the marsupials. I'll get to that too, okay? But that's where we get our teeth. We get our teeth from the bovine family and these artiodactyls and from the marsupials because they inherit the same amount of teeth from our ancestors that were four-legged. Before the four-legged animal, one of them had to stand up to survive, okay? Here's bite force, okay? So you have your orca, 19,000 psi, okay? The walrus has an 1,800 psi bite. That was actually a lot stronger than I anticipated. I had no idea the walrus had such a bite force, but he does. The elephant, 2,100 psi. The feline, this elephant seal, and tigers, they have a bite force of 1,000. 2,200, or 1,200, my bad, 1,200 psi. And at some point, see, the kangaroo, they have a 925 psi bite. That was a lot higher than I anticipated also. When we unlock our G unit, our gorilla unit, we can bite 975 psi. Typically, it's around 150, 200 on average. But we can, like if somebody gets in a fight, they can bite hard. Just saying, you know. Here's the gut, okay? So it starts with a foregut as the whale, okay? The even-toed ungulates evolve. They're foregut fermenters. They're ruminants, but pseudo-ruminants are gonna evolve too because that ruminant's starting to shift toward a hindgut fermenter. So they're pseudo-ruminants, and then a kangaroo is actually a pseudo-ruminant. He's losing it. He's a foregut fermenter, but he's losing it, okay? And eventually the hindgut anthropoids, like simians and ape, they're gonna evolve. Because there's not too many animals on the earth that are bipedal. And they're definitely not humanoid looking like us. The kangaroo has a torso like us. The koala has a torso like us. And, ape. So those are indicators. Because as these animals evolve, they get closer and closer and closer to related to us. But anyway, the bovine, he's foregut. Now the kangaroo, he's foregut. And the koala is hindgut. We're hindgut. So whenever we were going through our marsupial stage, we chose the hindgut fermentation. That's what we ended up with. Because our bites, our food, what we chose to eat changed. We had to eat other food, probably bugs and such. Carnivorous, All right, now here's the children's names. They're what we call the offspring of these animals, okay? So you have your whale. The male is the bull. The female is the cow. And then you have your calf. Hippo, bull, cow, calf. Bovine, bull, cow, calf. Goat, buck, billy, nanny, doe, or calf. A sheep, ram, ewe, or lamb. A kangaroo is a buck, a boomer, doe, flyer, or joey. An ape is an alpha and a beta, the male and the female, man and woman, Now what's cool about this is because, like I said, it's written in our language, our DNA. Our relatives. The manatee is also a bull, a cow, a calf. And an elephant's a bull, cow, and calf. The walrus is a bull, cow, and calf. But all the other seals, the earless and the eared seals, are bull, cow, and pups. Or tom, queen, and kitten. The seals are bull. They're not calves, cow, like us, and a bull, like all of these guys are. So even when it comes to labeling our children, we're still related to the artiodactyls and the walrus. You ever heard of the walrus and the carpenter? They get all these people to, they get these oysters. And basically, they dupe all these oysters to follow them, and then they eat them. As a matter of fact, you ever seen that movie Dogma? Loki's talking about that to Bartleby at the beginning. He's talking about the walrus and the carpenter, and he's talking, like Jesus representing the carpenter, and the girth of the walrus. That was, Buddha, I think. But here's this miles per hour here, okay? The cetacean. Of course, dolphins can swim pretty fast, 20, 30 miles per hour, I believe, actually. The walrus and the elephant seal, 3 to 6 miles per hour, okay? Now, in the hippos can run up to 30 miles per hour. The rhino can run 34 miles per hour. The bison can run 35. An antelope can run 61 miles per hour. And this is where I believe, because the antelope did stand up, and I'll get to that. I'll get to the antelope standing up, okay? Because it did happen to our bipedal antelope. Okay, I believe this is where the concept of pan comes from, because pan means upright walking. Chimpanzee, that's why it's called pan. Okay, so that's when we first started standing up was in artiodactyl stage. But I believe pan could run, this animal, Procoptodon actually, could run about 50 to 55 miles per hour. It's extinct now, but I believe this was the fastest bipedal animal to ever live. It was pan, and it really did exist, but it was Procoptodon. Anyway, I'll get to that. Okay, so the kangaroo can actually travel, jump-wise, 44 miles per hour. Of course, the orangutan, he's sluggish. You know, he's like the oldest ape that we're related to. The orangutan's like the baby when it comes to, you know, all kinds of stuff. When it comes to bite force, when it comes to movement, running, he's like the baby apes, and then they get better. So then you get to the ape, like a chimpanzee or a gorilla. They can run up to 25 miles per hour, and if they want, they can. If they have to, they can even exceed 25. That's as fast as Usain Bolt, which can run at least 28 miles per hour. You know, animals are no joke when they run, especially that antelope. Goodness, 61 miles per hour. It's amazing. Elephants can travel at 25 miles per hour. That's mainly because they have a large stride, because they have long legs. They're really huge. You know? So this is what I was talking about. The pinnipeds, their species rate, it's a lot lower than it should be. So whales, there's 90 species of cetacean. There's 270 species of even-toed ungulate. There's another 27 there. And the 90, 9, 18, 27, 999. Anyway, and the 330, 33, 33rd and parallel, 33rd degree Mason. Anyway, all right, so there's 33 species of pinniped. Of course, that 33, that's 330. That's the marsupials. Anyway, that's far lower than it should be, technically. It should be in the range of probably around at least 150 or so. You know, there should be, but they didn't take the extinction too well. On average, by doing the species, there should be at least about 100, 150 or so. There should be a lot more than 33 species of pinniped. But it goes 270 species of even-toed ungulate, 330 species of marsupials, 300 and plus. There's about as many marsupials as there are primates, okay, and they're roughly the same size ranges, and that's significant also. Size, biomass has to do with energy and conservation of energy and momentum, thermodynamics, and the conservation of evolution. There's 1,500 species of rodents, 1,400 species of bat. Roughly, they're about the same sizes and about the same species. Okay, the smaller an animal is, like I was saying earlier, the more it mutates, and the more species are going to evolve from them. Okay, so these large animals are going to dwarf smaller animals, and then when they pass dwarf mutations, like an event happens, these dwarf mutations are not going to be just stagnant like they are now, because everything's kind of complacent right now. Everything's pretty good, no real need to mass evolve or any kind of stress that's going on right now. So we're passing stagnant mutations because evolution passes these, or even nature passes these stagnant mutations because it's like it's keeping the exercise up, So it still passes the mutations here and there, and we have, mutations of people, bad or good, doesn't matter. But whenever something happens, a constraint, like if something really happens, we're going to start passing more mutations that are beneficial. They're going to be beneficial mutations. Because right now, like I said, there's no reason that we need to adapt yet. So our we don't pass beneficial mutations. Okay, so like the Mississippi, okay? So once Mississippi evolves, he's the largest whale, because this is the blueprint, That's why the blue whale is like the newest blueprint of the largest, oldest animal on Earth, okay? That's why the blue whale has such young DNA, but technically it's the oldest species of animal on Earth. Because it evolves slowly because it's so large. By the time it reaches now, the finalization of its DNA is being finalized. You know what I'm saying? So now it's a new animal. So the Mississippi evolves, has no echolocation. It's going to pass a dwarf species or dwarf gene that's going to mutate, and it's going to grow teeth. Echolocation is going to evolve. So he passes a dwarf mutation, Odontocetes evolve. Okay? Odontocetes, sperm whale, for example, passes dwarf mutations. Boom. Killer whales evolve. Okay? They get echolocation. And every time a dwarf mutation, the brain is bigger. Okay? So there's no echolocation here. The EQ is like 0.15 to 0.23. Okay? Mrs. Seddies aren't too smart. But a sperm whale is a lot smarter, even though he's still not as smart as the orca or bottlenose dolphin. Okay, so he's got the killer whale. He's 6 tons, 2.5 EQ. Once another mutation is passed, another dwarf mutation, you have a 4.0 EQ, which is the bottlenose dolphin. The brain just keeps getting bigger and bigger as the animal dwarfs new animal species. Is it still connected? Oh, but dang, it still is on. That's my daughter. She's staying over at a little friend's house. All right, so you have your dugong. Okay, so these are all in the ocean. These guys are in the ocean. These guys are in between, and then you get to the land. So it goes fully aquatic, semi-aquatic, land. It doesn't, current science says 4-legged animal pops onto the land and then just goes back to the water. I just, for some reason, I can't believe that. Anyway, all right, so let me just read this. These guys are earless. They're whales. They're earless, and they got 5 fingers. Okay? All the Sirenians are earless, and they got 5 fingers. Okay? Now you get to the sea lions. These guys are eared, and they got 5 fingers. Okay? These are the eared seals. You have the earless seals, and they got 5 fingers. All of a sudden, boom, you get your ears. Animals' ears are going to grow. Okay? This guy's got 5 fingers. Okay? The hippo. He's got the 5 bones in his hands. But they're going to split. Let's see. Right. The bear here, he has 5. The tiger has 5. The elephant has 5. And these are all, see, the elephant, he's suspended. Like, instead of laying flat like this, his toes are all hemmed up in a foot like this. And he's like walking on his tippy toes. That's how the elephant's foot's designed. All right, so this is why we're 90% related to cats and 80% related to dogs. Okay, so Odobenidae, like I was saying earlier about tracking the ivory. Okay, that's the walrus. This right here's true seals. Okay, these guys have no ears. So we're connected to the cats through the earless seals. So these guys are ivory. You track it back to the no ears, and they're pinnipeds. Okay, these guys are related. All 3 of these pinnipeds are all related because they're all pinnipeds. But these 2 are earless. Our guy, the walrus, and the cat's guy are earless. And these guys are going to evolve into cats, while the hippo's going to evolve the marsupial and ape. Okay? That's why we're first cousins with cats. And cats are like first cousins with dogs. But dogs are second cousins to us. You see what I mean? Because they're still related to the seals, our semi-aquatic roots. But they're of eared seals. So they're just a little bit different at our baseline of DNA. When it comes to old DNA. It's like old money, but it's old DNA. The older you get, the baseline, there's going to be a lot more shared, All right, so this is how they have right here. So what? It just, evolved into a damn circle? I mean, I'm just saying, that doesn't make any sense. What is this? It all evolves into a circle? What? These guys mutate into this mutates into that? What? It just, he does in a circle? Whenever you do the biomass here, the energy, it doesn't make any sense. Now, if you take all the animals, now I haven't even done this because I've only equaled up to under or close to the mass of the whale. But taking a male and a female from all the biggest species of mammals and add them all up, add all their weight up, you're still not going to you're not going to get the exact same. You're going to get equal to or less than the weight of the whale. So you're not going to exceed the original progenitor's energy mass. You see what I mean? When it comes to energy and physics, a whale can't evolve from a mouse. It just can't. It cannot happen. That's impossible. It's impossible. I mean, but I don't think they expect anyone else to know better. So when they say this stuff, oh, a whale evolved from a mouse, they don't expect anyone to know better, and they're just going to accept it. I don't do that. No damn way. I used to believe the same stuff when it comes to that, but it never made sense, and I always found holes in it. And every time I tried to make theirs make sense with it, another hole would present itself. And then one day an epiphany just struck me, and I started thinking how I used to think when I was a kid. Because I used to think simple like a kid. When I was in 2nd, 3rd grade and stuff, I thought that all the mammals of the land evolved from the mammals of the ocean. I literally, as a child, for the longest time, I thought that. And then science, whales evolved from a 4-legged animal. So I scratched that theory, and believed that shit for so long. And then finally an epiphany came back. You know what? Just look back into that. And lo and behold, I mean, I'm adult now, and we got a lot more information, and it fits so much better, especially the DNA. The DNA makes perfect sense. And you can even just follow the DNA. You don't even have to follow the fossil record. You can clearly see our evolutionary line. Anyway, here's a sperm whale's arms. Here's a manatee's. Of course, I didn't have enough room. But ultimately, you see where I'm going with this. These guys are marine, and this is going to be early phalanges that's going to evolve. And anytime an animal comes out of the water, they're going to have hooves. Just like Mesonicid, that's a hooved wolf. At some point, when we were coming out of the water, the wolves, different, dogs, cats, all those animals, everybody came out of the water. We go through a hooving stage first. So a wolf with hooves is not wild at all. It's not insane at all that there's a hooved wolf. It's not insane at all that there's hooved marsupials. But I'll get to all that. It's just, you got to know where to place it. And it's like I said, if we understand our DNA and our polymorphic evolution better, we will understand how to treat diseases. And I'm just going to throw this out here, okay? I believe we will figure out obesity. That'll be one of the first things we figure out is obesity. Because we evolved from large macrocosmic animals, basically. You might say macrocosmic. On a large scale, it's a macro evolutionary scale. So it's a macro animal. And they have whale blubber, I mean, there's genome in there that we can, well, if we understand how we evolved, then we can start picking up on why we have a lot of these genomic problems and what animal correlates through whatever evolution. I mean, we would actually be able to treat a lot of diseases like acromegaly. That's another one I believe we'll figure out. We'll be able to actually understand, okay, so there's something in our DNA that's doing this to the pineal gland. And then I believe that we will find something in one of the large animals like the walrus or the whale that can help us understand acromegaly and how to treat it. Because the brain of a whale is technically stem cells. I believe that was actually what Magellan was looking for. When he was looking for the Fountain of Youth, I believe he was looking for the sperm whale's brain, and he didn't actually realize it. Or he did, and we're just not told that part of the history. But the bovine, like we're the part of the bovine. The Egyptians knew this stuff. The Greeks knew it. We're related to the bovine. That's our beast of burden, because we are a beast of burden. We got the same amount of teeth. We only have one less bone. And we're 84% related to the cow, and we're 96% related to a pig, which is nuts. But it's not crazy at all, because we're related to artiodactyls, which are related to whales. And they all came out of the water, I mean, we all came out of the water. So by the time it gets to this stage, see how the nostrils are on the front of the face now? They're not on the top of the head like they were on the hippo. They finally managed to move to the front of the face. You see? And this is where we get our filtering from. The little angel kiss right there above your lip? This is where we get it through this stage right here. And this is actually where we get our goatee. And that's why we even call it a goatee. Because this is going to be one of the stages. Now imagine, of course, like I said, the Greeks knew this stuff. Imagine Pan, he's got horns, a little demon and all that. That's where the concept of demons and stuff came from. And centaurs and, Pan and all that stuff. I mean, these people knew. We've just, in thousands and thousands of years of word of mouth and, change of this and that, and it all gets put in these mysteries that are just, completely turned wild and crazy, and then ultimately it turns into a big story that just, it loses all of its truth, See, we have 206 bones, they have 207, but we also have 32 teeth, they have 32 teeth, they have 20 baby teeth, just like we do. Milk teeth. The antelope, he's got 32 teeth, obviously. course, these guys, see, this is where we get that from. Our filtrum. Now, this is the antelope that stood up, okay? There are species of antelope that, like I was saying, the necks had to grow with the giraffes to reach the high food. Well, one of the artiodactyls, because when I was looking through this, I asked myself, I was like, I wonder if there's a species of artiodactyl that's bipedal. There has to be. When I looked it up, lo and friggin' behold, man, there is. And I was like, holy crap. And there's actually an ancient tree of life. If you look at the ancient tree of life, you'll see the antelope on it, standing up. That's what led me to it. Because I saw that and I was like, because it's the Greek and it's the ancient tree of life. And I was like, whoa, what are those? You know? And then I kept reading. It was like they were artiodactyls. They were antelope. And I looked into it and lo and behold, you know, it just seemed to fit too damn well to be some kind of coincidence. So this is where we start getting our axial plane. Because this animal, I mean, they had to survive. And this is going to be the earliest stages of vertebral, or at least y-axis standing. You know, instead of crawling x-axis, we're up, vertebra, y-axis. Vertical, you know, vertebra, vertical. See, it gives a whole new concept of this stuff. You know, it's, yeah, of course, a little half-goat man didn't exist that played flutes out in the woods, you know, but I'm sure this thing did evolve. It had to. I know it did. And then that gives a concept right here. You know, these people knew that we were related to the bovine. And here's a horse. Of course, the horse, if you look at our finger, if you look just like this illustrates, it's got all the exact same bones as our middle finger. And that's why we have, our fingernails used to be hoof. You know, that's where we get these from. They were claws at some point also, but they originally began as hoof. Before the fingers and they end up splitting, because that does happen. Like bifurcation on a tree, it will fork. See, and this is these animals are going to stand up, and they're going to be standing for so long, they're going to utilize different sets of muscles, and it's going to put constraint on their bones. And eventually it's going to force the bones to actually have to change. So this is going to become flat. So it's going to end up becoming flat like this on the ground, and this toe the foot is going to recede, and all this hoof down here is going to end up as toenail. These people knew something. All right, so right here it says humans share a recent common ancestor with rodents, but the genome is more cow or dog-like. Okay, that was when I took that note. And I was like, it's more cow or dog-like. Well, the cow aspect has to be the whale, and the dog aspect has to be a pinniped. And if you put those together, you get the walrus again. Because he's related to the dogs, because he's related to carnivoran. So that's the dog-like DNA that is showing up here. But it's also the cow-like DNA that's showing up because the whale. You see what I mean? So if you use the DNA after you work out the chart, the grid, you can start putting the DNA together. The DNA starts falling into place. You know, the fossil record, too holy. It can give us a baseline, but ultimately we can only get a baseline because, you know, less than 0.01% of species even survive, and less than that fossilize. You know, so it's hard to use a fossil record that has so many holes in it. And it just creates confusion, you know. Just use the modern science. Stick with what we know. That's what I'm doing. Stick with the animals that are alive now and the science we have now, and just use those, you know. Just use those. See, like this right here. This is how I was talking about the manatee is the stage of evolution where the front limbs are going to evolve first. See, when tadpoles evolve, or well, grow anyway, their hind limbs come in first, and their tail's receding. And then their front limbs come in, and their tail's even shorter. See, ours is going to get shorter, our tail is. The front limbs are going to evolve. Through the pinniped species, it's going to get even shorter, the tail is, and the hip's going to get bigger, and then it's going to split into two back legs. You see what I mean? And it's going to come further inland. And then you're going to get four-legged animals. See, here's another aspect right here. The tadpole growing into an adult frog, and like a sperm whale, the sirenian, the pinniped, and then a four-legged animal. You know? So evolution works the same way, but on different scales. You know, it knows what it's doing. It's really intelligent. I mean, if we actually just look, if we take a step back, because we've been adding puzzle pieces for hundreds of years right now. There are puzzle pieces just laying on the, I call it just a cluster mess, you know. But if we take a step back and start trying to put the edge pieces in, and we can start putting the pieces together, you know, because they're just cluttered right now. We've been throwing pieces on the puzzle instead of putting them into place. But if we take a step back, start putting them in place, you know, we, you know, make more sense out of our DNA, I believe, you know. See, this is the 300 million years, like the lobe-finned fish coming to land, okay? 100 million years go by in the 200 million year lineage. The ichthyosaur evolves this way. Of course, we're still going to be coming to land, therapsids, okay? It's going to continue to evolve. Evolves into a whale, boom, comes out of the water. This 100 million years is four-legged animals. You see what I mean? So when we're evolving this way, we're getting better and better and better. And every time these animals come to land, they get better and better and better. And since DNA is a memory bank, the blood remembers, then it knows the same tree can grow back, but twice as fast and twice as accurate, twice as more, twice the model of animal, you know, 2 times as more efficient than it was, you know. So it learns every time, you know. See here, the amphibians, reptiles from the lobe-finned fish, but he diverges down. The ichthyosaur, he comes out, cynodonts, therapsids, continues the whale, boom, modern artiodactyls, marsupials, man and such. See, here's more of the feet with the bovine. See how this splits? You know how Spock live long and prosper? Live long and prosper. And this thumb right here is just a little vestigial nub right here. See? Spock. I believe that's what, you know, just saying. It's not arbitrary, you know. There's all kinds of subtle stuff in Hollywood that they just give us that they'll be like, oh, they'll never know what it means. Yeah, I mean, maybe I don't even know, you know. I still don't. That's just what I'm attributing it to, you know. And these animals are bald. Whenever we come out of the ocean, we're bald. Just like an animal, whenever a baby's born, they don't have teeth, typically, or they're bald, you know. Sometimes you can get a baby born with a couple of teeth. Sometimes you can get a baby born with a real head full of hair, you know. But it's rare. Typically, on average, babies are born with no teeth and they're bald. So when it comes to evolution, it's no different. The first animals that evolve, the largest animals, they're not going to have any teeth. And they're going to grow teeth when they pass dwarfing mechanisms, you know. And they're going to be bald, too. And our hair is going to grow in. We're not going to lose it. A four-legged animal with hair isn't going to just jump into the ocean to become a whale and lose all of its hair, you know. So, again, you know, we can clearly observe when it comes to evolution the same stuff that we see in everyday life. When it comes to tadpoles, when it comes to growing, humans being born, whatever, it's all the same. Evolution knows exactly what it's doing. Here you go with the antelope. We call this the antelopine kangaroo because he shares so many phylogenetic traits with the antelope, coincidentally. Now, is that just a coincidence or what? You know, that the antelopine kangaroo is called the antelopine kangaroo because he mirrors the antelope. Okay, now look. Now this is a theory. I'm going to get to Procoptodon. See, here's the hoofed kangaroo, Procoptodon. He's extinct. But ultimately, the hind limbs are going to be evolving. So this is going to be one of the stages of evolution. This is one of the transitions. Okay, so this is a theory, but it makes sense. It sounds a little weird, but I'm just going to throw it out here anyway. All right, so whenever the antelope or an artiodactyl begin to stand, its udder is going to eventually invert, okay? After a while, it's not going to end up using it because the hips are going to have to re-evolve. Because now the animal's standing up, and it's going to have to use, it's got a whole bunch of different kind of constraint on its hips. So it's going to force an evolutionary response in the hips to be able to, it's going to re-evolve the hips to be able to give birth to a full-term placental. But during that transitional stage, it has to evolve into a marsupial because it's going to have to re-evolve the hips, okay? Now, the udder is going to get absorbed, and the 4 teats on the udder are going to get inverted, and that is going to become the pouch. And the teats are going to invert to the inside of the pouch, and there's 4, okay? So they have 4, and the kangaroo has 4. And that udder is going to evolve basically into a pouch. And this is why Pan is a sexual god, because this whole stage has to do with the uterus, the mammary gland, the hips and birthing mechanism, and not to mention a artiodactyl that stood up, you know? So it all fits together, you know, if we suspend disbelief. And the diprotodont, this is the species of marsupial that we're related to, the diprotodont. Without the diprotodont, we might not even be here. And I'll get to that. Okay, this is polyprotodont. Yeah, he's the bandicoot. He's related to us, but he's not the guy that progenited us. The diprotodont is the species that progenited us. That's our marsupial. Just like the walrus is our pinniped. Okay? Now, I'll get to it. Well, of course, you know, the uterus and this. I just believe this is a perfect example of misinterpreted ancient knowledge. I mean, it's got all the same stuff I'm explaining. It's got all the same characteristics, but it's, you know, it's said in such a way that it doesn't sound favorable, you know? Just like Baphomet, you know? It's an artiodactyl. It's because we're the pinnacle of evolution, you know what I mean? And it coincides with demons and all that, you know? It really easily coincides with demons. And Greek mythology, the Romans, Roman mythology, all of that, it's all connected. It's all connected. But they knew evolution. They knew the path that we came out of the water, and they knew that we were related to every animal. And here's another thing when it comes to evolution. Okay, well, at least when it comes to the lizards and the platypus and sauropods like horses, okay? Now, lizards, their shoulders and arms are positioned to their sides, and they move in a side-to-side fashion, kind of like a fish swings its tail side to side, okay? Whales, they move their tail up and down, like we would move our legs, if we were four-legged, forward and backwards. And they're positioned under them. So this is technically a sauropod. This is a tetrapod. Now, this is a tetrapod also because it has 4 limbs. Okay? So all sauropods are tetrapods, but not all tetrapods are sauropods. Okay? And there's a lot of sayings like this, like all axolotls are salamanders, but not all salamanders are axolotls. Okay? Stuff like that shows up a lot when it comes to biology. So there's a lot of things that we need to reclassify. Because if we can say stuff like that, that can create a confusion. And we don't want a confusion bound. You know, we don't want any boundaries of confusion. So, you know, we don't want to cross any paths of confusion. So if we can relate the information in a more accurate way, just like the ethnicity factor, you know, if they can hybridize, even if they're of a different species, they're not of a different species, they're of the same species, they're just of a different ethnic group. You know, I mean, right now they got it labeled like a European American and an African American are 2 different species of human, but they're not. You know what I mean? That's literally what they say about the animals, but it's untrue. These are all therapsids. You can see how they're mammalian because their legs are positioned under them. Now, obviously, they have reptilian traits, but their legs are positioned underneath them. Okay, that gives them more of a they're all synapsids also. They're therapsids, but they lay eggs. They're like in a transitional stage. This was the hundreds of millions years ago. Well, the 200 million years ago. There's a 300 million year period, a 200 million year, and a 100 million year. And each, what I call a macrocentury, transitions. See, here's a horse. They're positioned under them. Their shoulders are positioned under them. So they're technically a sauropod. They're a tetrapod, yes, but they're technically not what you'd consider a tetrapod. They're a sauropod. See, these are a tetrapod because they move in the side to side and their legs are on the side. Just like the platypus. See, the platypus is not a mammal. It's got a superficial mammary gland. And it's endothermic, but it's an endothermic reptile. It's a mammal-like reptile, whereas the ichthyosaur was a reptile-like mammal. And subtle things like this can cause a lot of biological confusion when it comes to evolution. See, here's another monotreme, the echidna. He's got his legs positioned to the sides also. You see, so it's there, and they lay eggs. See, and also this guy lays 1 egg. So the more closer to human, humans lay. Well, they don't lay egg. They have 1 offspring. All the big animals have 1 offspring. Okay, the closer this thing gets to being mammal-like, and then after it evolves like through the platypi stage where it's still in the water, you know, the platypus will lay like 2 eggs in some cases, 1 sometimes, you know, but it's typically about 2 eggs. It's getting closer to being like a human. Once it comes to land, now it's an endothermic reptile and it lays 1 egg. It only has one offspring. So it's getting, it's gaining those traits the further it evolves. It's gaining more mammal-like traits, but it's still not a mammal because it doesn't have a placenta. And that, like I was saying, the placenta problem in evolution, scientists won't even go near. And if you explain it like this, it completely solves the placenta problem. The placenta problem doesn't even show up, as a matter of fact. And triangulating the area, see, since all these marsupials came from this area of Australia, and the oldest ape that the oldest ape that lives right now is the orangutan. He lives in Indonesia. That's just north of Australia. That indicates to me that technically Australia was so far down under that the KT extinction didn't hurt it as bad. The rest of the world took the KT pretty bad, but Australia was down under enough that it had a little cover to it. So a lot of these marsupials did survive, And eventually, one of them had to end up going into the trees to be able to eat. And there's the tree kangaroo. The tree kangaroo is diprotodont. Talude bear, it's a diprotodont. The koala is a diprotodont, and so is the kangaroo. It's diprotodont. Okay? This is significance because that diprotodont is our marsupial. Like I said, the walrus is our pinniped. Okay? So that diprotodont species is going to have to climb into trees. Now, when it comes to the shoulders here of the kangaroo, okay, now he's humanoid-like. You see? Now he's got the torso of a human. It's getting closer and closer to human. Now you can see how his clavicle isn't as broad and as long as our shoulders. You see how it doesn't have the gorilla or the human-like shoulders here? Now he does have a torso of a human, but his shoulders aren't developed yet because he hasn't had to go into the trees to survive. You see how the clavicle isn't necessarily as evolved as ours? Because he hasn't been an arboreal animal yet, but he's going to get there. At some point, they had to go into the trees. And the tree kangaroo is an actual animal. It's called the tree kangaroo. And koalas, they are arboreal, okay? So over time, that marsupial animal gets more human-like. Now the shoulders are starting to evolve. Even the fingerprints through the koala stage here, even the fingerprints are indistinguishable from ours, okay? This is another clue because every time you get an animal that looks more human, you get more of a human trait. So evolution is working toward mankind. See, here's the bicep and tricep. It looks just like ours. And the thumb is even going to move up into place. Just like the toe here eventually is going to move up into place when we come back out of the trees to live on the land. And that does happen too. Because the ecosystems that we chose to use to survive dictates what traits we're going to evolve. And that's epigenetics. Okay, so the epigenome is being programmed and convergent evolution is happening because all of these animals are sharing arboreal life. So they're going to have a lot of the same traits, but those are also our traits. So we got to consider that. We can't just say, oh, it's just convergent evolution that an ape shares a similar hand to a koala. It doesn't mean anything. It means a lot to me because this hand is so close to human, it's not even funny. So when scientists quit spitting in the face of science, maybe we'll start figuring this stuff out. I'm just saying, okay? And then this is a koala. Look how close to humanoid this thing is. See, even the fingers, even the hands right here, you could easily confuse this with a simian. You could easily confuse this with a baboon or a monkey or something. But it's not. It's a marsupial. It's a closer form to us. But it's not quite ape yet. It's getting there. Even the koala, see, whenever he's on four legs, his legs are positioned under him. See, we never actually had this sideways positioned. We never went through that family. We're related to frogs. We're related to them all, but they're in a completely different lineage altogether. And scientists will lump the humans and mammals into the same family. They lump it all together in a big pile, and just say, and call it a day. You know what I'm saying? Instead of organizing them and putting the ducks in a row, they just clump it all together. It's like the singularity. The singularity actually had to form. But all the science they have when it comes to the singularity forming and the universe's birth and everything, they have it all piled onto each other that there's no clear picture. And then they make it so hard to imagine that nobody can get a clear picture from it. You know what I mean? So then it leaves a bunch of people with more questions and confused than answers. And I've heard even a lot of these guys say, whenever we figure something out, it leads us to more questions. It shouldn't do that. Whenever you figure something out, that's a puzzle piece that you got put into place. That's less pieces that are on the table. That means you got less on the table and more into place. So it shouldn't give you more questions. It should solve more answers. You see what I'm saying? So, I mean, and you can't look at the universe like it's numbers, you know? Yeah, numbers are a way to read the universe, but you got to look in action, okay? You got to read the universe by observation, okay? Then apply the numbers. See, I can speak by speaking. That's my action. But I can describe that with a language by typing. Just like the numbers would be the typing aspect, the language that you're describing of the action, you know? The numbers can be misinterpreted because if somebody's typing something to someone and they're thinking it in a certain way, somebody else could hear it in their head a different way, you know, that's not being meant. So, I mean, everybody's done that. We'll be talking to somebody and we'll think they're saying something and be like, oh man, why'd you say it? And he's like, no, that's not how I meant it. And then they'll have to explain how they meant it because you couldn't hear them say it. You see what I mean? So whenever it comes to just the language, you can read the language, but you're not going to get the same exact result because, you know, you might be interpreting it different. You know, it's differently because, I mean, we got paradoxes in our math. We got a lot of paradoxes in our math and science. And that's why, because we're interpreting it in different ways when it only applies one way. But we don't know the fundamentals to be able to apply the math. You see what I mean? Like the scientists got all the math laying around, but now they don't know where to put it. It's like, oh, well, we got 6 divided by this or that, right here. Then we got this divided by this right here. Where do we put all this math? You know, but if they have a baseline to go by, a grid that understands fundamentals, they'll understand the fundamental lays here, the fundamental lays here, fundamental lays here, fundamental lays here. Now you can put your math in where it goes. You see what I mean? Without the fundamentals, we don't know the math. The math can just be some random numbers. Well, what do these numbers apply to? Well, I don't know. We're going to have to find out. You know, it's like, well, if I know what the numbers apply to, and I can apply them a lot easier. You know? So whenever the continents broke up, see, whenever the KT happened, it's about this time, we were down here in Australia, and it was still moving up toward Asia. So I believe pretty much what happened is, whenever we started moving up in here, this is where the oldest, like I said, the oldest ape that live right now are the orangutan, okay? So by using that pattern, the oldest ape comes from here, old world monkeys come from here, and the marsupials come from here. And if these all guys are connected, it indicates that we spread up through here when we become more ape-like and spread up through here more and more and spread out all through this continent and evolved into many different species of humans. And ultimately, by the time we reach this area here, we had converged, all of our DNA had converged, and one species remained. You see what I mean? So we evolve, we spread out, and then we converge. And we always tend to follow the sun. We all animal. It's the pattern that I keep seeing in this is that all the animals every time they always tend to follow the sun. Even on a evolutionary scale here, when we spread up north, we spread northeast or northwest. So we were following essentially, you know. I mean, I think we follow the light naturally anyway. You know, it's kind of like a bug. Moths follow the light. You know. It's just a natural thing to follow the light. See, this is Sunda and Sahul. A lot of people have never even heard of this. This is actually ancient Indonesia. This is when Australia had a lot more landmass because the oceans were a lot lower. And Sunda here, there was a lot more bridge here for these animals to actually get up into Indonesia and up into Asia and Europe. So this ties into this. Of course, once the continents broke up, you know, you're going to have marsupials down under. Then you're going to have few survive, like the opossum, in North America. Now, the funny thing they say about this, and I'm just going to throw this out here, because scientists claim that even though 30 million years ago this was about 1,000 miles apart, still 1,000 miles of open ocean is treacherous, okay, especially for a monkey, all right? So if they say monkeys rafted over from here to here, I kind of believe that's ridiculous. I believe what happened is, and there's this theory too. This theory is actually out there too. That when this broke up, there was still a marsupial remaining, or a few of them, very diverse. Like I said, the KT hurt them badly, but all the marsupials down here and down under, they were pretty protected. Okay, so those marsupial evolve, which are rodent-like, like the possum. Now, the possum has a prehensile tail. That means he can use his tail for a limb. Now, all these monkeys down here, they do the same thing. And here's the possum's hand. Okay? So what I theorize is because of DNA, because DNA knows what it's doing, like the marsupial evolved ape-like over here, the marsupial is going to do the same thing over here. So the marsupial is going to evolve more toward a simian form. And that's why all these New World monkeys look like rodents, because they're related to a marsupial that's kind of rodent-like. Whereas our rodent, the macropod, the kangaroo, wasn't as rodent-y-like. You know what I mean? So these guys are going to have way more rodent-like traits than us. But we're still related to the mouse, too. And there's that. I can get to that. I'll get to that. Well, I might be able to get to that. See, all of these guys. Okay, now this right here, this is a gene pool grid that I made. All right, so the depth of the water as the animal is big. This is the animal as a big animal. And the depth of the water here where it's shallow, it represents the animal as it gets smaller, because like I was saying, dwarf mechanisms are passed, okay? Now, this right here, because we all have mammalian genes and reptilian genes, whether we're a mammal or a reptile or not. We have inverted genes. Like they have reptilian genes, subtle mammal genes. We have mammal genes and subtle reptile genes. Just put it that way, okay? And we see that whenever these animals like the monotremes evolve and such. But anyway, so this tsunami, whenever the animal gets smaller and smaller and smaller, its secondary genes become more prominent. Okay, so like right here, as reptiles evolve, mammalian traits emerge such as warm blood types, insulation, hair, feathers, the platypus and duck. So the mammalian traits are becoming more prominent the smaller these animals get. You see what I mean? Now, whenever it comes to us, the same thing's going to happen. Our mammalian traits are going to become more prominent the smaller we get. As mammals evolve, the reptilian traits begin to emerge. Armadillos, how they have like leathery, scaly skin. The pangolin, porcupine, beta-carotene from the reptile lineage gives reptilian traits to these animals. See, we have alpha-carotene and beta-carotenes, but the reptile lineage is primarily a beta-carotene lineage. Okay, so beta-carotene is what forms feathers and scales, whereas alpha-carotene, because we're alpha-beta, the mammals are the alphas, the egg layers are the betas. We have the alpha-carotene gene. Now, we have beta-carotenes, but they're very, very subtle. The bat, okay? This guy, Dermoptera, okay, look. This is a theory here, that these marsupials that lived in trees, eventually when they get small, of course they got humanoid characteristics, and that's why the bat has humanoid-like characteristics. These marsupial that are totally humanoid-looking now are going to get so small and helpless that they're going to have to evolve a mechanism for survival. And that's going to be flight, okay? Now, rodents, on the other hand, they evolved a different mechanism. They have a bunch of babies every time, every litter, okay? And they can have several litters per year. A mouse could have like 100 babies, 80 to 100 babies a year, okay? That's their survival instinct, their mechanism, okay? But the bat, it only has one offspring like us. And with that kind of, being as small and helpless as a bat is, and only having one offspring, that can hinder its population greatly. But evolution isn't a fool. So it adapts the animal to be able to fly, that way it can spread its genome and not go extinct. And that's why, there's as many species of flying bat, a flying mammal as there are rodents. But one of those marsupials progenited the simian, which is us. They progenited the bat, and they progenited the shrews, and they progenited rodents. But shrews are actually related to elephants. But it's not unusual. It's not unusual. Like I was saying, it might seem weird that, aardvarks and elephants are closer, but it's not unusual at all. See, this is a squirrel here. It's a rodent. Here's a rat. They have almost the same skeleton. Now the squirrel, it's like the smartest. It's got the biggest EQ of the rodent. Okay, the mouse has actually got a large EQ, but the squirrel, these guys, they store their food. They use tools. I mean, these are like the humans of the rodent world, whereas dolphins are like the humans of the ocean, and humans are the dolphins of the land. Here's a hare, the rabbit. Its mechanism of survival was to have a whole bunch of babies and never stop breeding, If it wasn't for those two factors, evolutionary factors, the rabbit would have been long gone. It would have been stew for every animal on Earth. And like I said, okay, this right here, now we have 27 bones in our hand. We have 27 bones in this hand, okay? That's 54. Now, we have 26 bones in our feet, but technically 2 of them fused in our ankle, okay? So we could actually support the weight of our body. So there's technically 2 bones in the ankle there. So that would be 27 times 4. That's 108. And that's, the significance with the 108, suns and the 108 moons and, all the measurements turning out to be 108. See, look at the baboon's feet. He looks like a little person, a little mad person. All the faces of primate here. See, they have their ethnic groups too, when you think about it. Now this right here, see, this is a baboon, or this is a mandrill, all right? Now I go with the size of these animals, okay? You gotta go with size because mass is everything, size and energy. So the mandrills, actually, they're mandrill that are ape. They're not ape, but they're monkey. They're simian form. These guys weigh as much as bonobos, okay? So even chimpanzees, bonobos, chimpanzees, and heavy mandrills all share weight ranges, so it's significant. Now, this right here, we all know how the mandrill's nose is like one of the weirdest looking noses there is. But this is going to be our cheekbone. This is going to scoot to the side here, and this is going to be more prominent. See, that's where it was. The face is going to get flatter, and that's going to move over and become, boom, that right there. So it's not just this little small piece of bone right here, like it is right there. Now, since this moves over, a whole cheekbone evolves. A whole cheekbone comes to be, which gives us our cheekbone here. And when you triangulate this, see, Pithecus, he's orangutan-like. It's 12.2 million years old, and it was found here. So this is where they found the oldest fossils of humanoid in Ethiopia. It's said to be, And then this is where the oldest ape that lives, the orangutan, lives, okay? So what I did was I triangulated this. I drew a line for here, straight up. And right here, Pithecus, 12.2 million years old. Dryopithecus, Ramapithecus, all these are like orangutan, but they're not orangutan. It's orangutan on the way to become a better humanoid. And as it goes through all these environments, it's learning new traits, it's picking up new skills, and advancing. And we literally spread all over these continents. Spread everywhere. And like I was saying, eventually we converged into one genetic pattern. You see, remember how I was saying the clavicle isn't evolved as much on the kangaroo? It's because they hadn't hit the trees yet. They hadn't been arboreal. So by the time we came out of the trees, that whole clavicle area here had evolved, and then we got broad shoulders. That's where we get our broad shoulders from, because we were arboreal. And because a marsupial had to go into the trees to survive. See here, this is our buttocks. Obviously, it looks like the fluke of a whale. This right here looks like the back of a whale here. This is our thoracolumbar fascia. And this right here is where our actual dorsal fin used to be. See, you ever see those, okay, you've seen Free Willy, or any of these orcas that are in the circus and stuff like this, or, doing tricks for people. You see how their dorsal fin, find it right here. All right, see how their dorsal fin is weak? Basically, that's what happens to our backs, because we're in unnatural situations. Now, we're hard workers, okay? We're worked to death by the government, it gives us bad backs. A lot of other people don't do enough work. And it does the same thing to the exact same spot of the back. It deteriorates it because of the torso, the weight of the torso. This right here helps these animals swim straight. Our lower back helps us walk straight. It keeps us in a straight, like if you have, I don't know, I'm just going to throw this out here. Let's say a person gets pulled over and they got a bad back, okay? They have to tell those officers. The officer can't necessarily say, oh, well, you got to do this test here, and because you fail, you have to be drunk or something like that, because if a person has a lower back, that's very bad. They tendency have nerve pains. You know, it's hard to walk a straight line. You know, so the back aspect right here is the same thing. You know, it's an unnatural setting for these animals. You know, they're not supposed to be doing tricks for, you know, humans, and, you know, and in some little small enclosure, not getting enough exercise whenever they need the right kind of exercise. You know, it puts too much strain on the back, just like it does us. See, that right there is the muscle, and it's made of the same material. It's a muscle on these animals' back that there's the residual. It used to that used to be us. And this right here, this is the pinniped here, and the Serenian. Of course, I was doing the muscle. I was trying to look in the muscle and the glutes, the gluteus maximus, right here. Of course, it's very, very primitive because they haven't hit the land yet. You know. See, and here's the fluke of it, and it looks like the muscle here. See, our spine comes straight down right in between. That's where our tailbone is, right between our butt cheeks. This is exactly where the whale's spine comes to an end, right here, right in between what's going to be our butt cheeks after this recedes and this splits and becomes the two butt cheeks as the animal's legs get better and better. And I mean, it's just a theory, but I mean, the morphology makes perfect sense. Like I said, a scientist would look at me and be like, "Oh, you're crazy," but ultimately, you know, I would debate any scientist any day. There we go again with our dorsal. I like this picture. I think it's really cool. Dorsal fin here. Now, I'm just going to throw this out here when it comes to wax, earwax. The earwax is a smoking gun, okay, that we evolved from cetaceans. Now, you know, a smoking gun, whenever it comes to the pyramids, there's water erosion. The pyramids are in a desert, okay? That's a smoking gun that indicates, and that's not just an opinion, that is a smoking gun. That is actual proof that those pyramids were there when there was water and it wasn't a desert, okay? There was rain. This is the same way, okay? These animals have the same cochlea and ear that we have, and earwax. We evolved from these guys, therefore all mammals will have earwax. That's the water insulation for our ears. And animals like the fish, see, the fish, they technically don't have external ears. Their eardrums are inside their little heads. Okay? So whenever the evolution's occurring and the ear diverges and the ichthyosaur evolves and then the whale evolves, these ears are going to become a well-adept water-insulated ear because it's evolving in the water from a fish into a fish-like animal that's getting closer to mammal, and ultimately it's going to be a mammal, and by that time, that ear has evolved into a little hollowed out ear with wax all through it that's completely insulated from water. I mean, you know, this is one of, and I'm just going to throw this out here also. I don't know if y'all remember when I was talking about the planet being a mollusk. Okay, our planet is actually a gastropod, and it has to do with the octopus too, because our planet is a gastropod. It's a pod of gas. It's a crustacean because it has a crust. It's an invertebra because it doesn't have a spine. It has a mantle like the snail and other mollusks do. It forms cave pearls with calcium carbonate the same way that pearls are formed inside mollusks. Okay, everything indicates that our planet is actually a mollusk in nature. Okay, if it was an animal, it would be a mollusk. If it was a cell, it would be a blood cell. Okay, that's what our planet. Okay, now with that being said, the octopus is Earth's version of itself, whereas humans are the universe's version of itself on Earth. We're the universe hemmed up in a human body. The octopus is the Earth hemmed up in a little body. And that's why the octopi is such an alien animal. The sporation aspect, that it came in and all that stuff, that's not far-fetched. That does have truth to it. But I'm going to end up diverging. Okay, anyway. Here's our eardrum. Look at and notice it looks like a mollusk. The sound. You know how you put a shell up to your ear and you're supposed to hear the ocean? It's an old, it coincides in an old way, with the sea and the sound, because the waters of the earth birth life, just like the female waters break to birth an animal. The waters birth the life. Not to mention, water where it meets the land, it's called the birth. So even a lot of this stuff ties in. As weird as it sounds, it ties in. Now, I'm just going to throw this out here. Okay, now this has to do with more of a physics aspect instead of biology, but it ties into the biology. If I can find where it is. I'll be up here at the beginning. Hell. I know it's in here. Here we go. All right. So, imagine a void of space, okay? Just a void of empty, dark, infinite space. Now, there's nothing that's going to be there except for sound frequency, because all sound comes from light and all light comes from sound, okay? Because sound and light go hand in hand. And whenever you have just an infinite dark void, it's loud. It's space roar. It's basically synchrotron radiation. Now, whenever a quasar is emitted, all right, they're always at an angle perpendicular of another quasar, okay? This means that these will always eject an emission pattern that will cross the path with another. Okay, and in the square area of space, this indicates Rotarian mechanics will formulate a new universe. Now, using this sound, you're going to get the golden ratio. Okay, the sound, the golden ratio. Look at it; it looks like a conchlea of the ear. So, and it's the waters of space too. On top of that, which is another aspect that kind of coincides. And it might seem weird, but it's deep in our physics. All life and physics of the universe, they're all going to mirror, because the universe is a living organism. Time began 13 billion. Life began 13 billion years ago. It only makes sense that there's life inside the universe, because every star and every planet, it's all animation. Imagine the cells inside your body. If all the cells inside your body don't exist, then you don't exist. Or if they're all dead, then you're dead. I mean, all the cells inside your body make you who you are. All the living animation inside the universe makes it a living universe. You see what I mean? So if there's no stars inside it, then it's not alive. There's no animation. There's no heat. There's no warmth. There's no endothermy. Because the universe emit is time backwards. It emits time, and it emits black body radiation. And we emit black body radiation because we have a thermal temperature, So we're going to mirror that same aspect. Okay. Hold on, let me get back where I was at. So the sound aspect coincides with the mollusk, which coincides with physics and sound and water, and the octopus, technically, because the octopi. That's our brain. That's going to become the precursor. The octopus it's Earth's version of itself, not to mention it's a precursor to the human brain. It's like evolution, like I was saying, it's working things out in the ocean, and it's like, all right, I'm getting the stomach built, I'm getting the brain built, I'm getting, all this stuff built of these animals, So, let's see. I'm just going to throw this out here, okay? So, Einstein said that the spatial dimension is finite, and he said the temporal dimension is infinite. But that's actually backwards, okay? That's actually backwards, because space has no beginning and no end. So if you can imagine imagine this white paper is just black, dark void. Now, where can I start measuring time? I can't. There's nothing I can measure except for just empty, infinite area. That means it's an uncreated creator, or it simply is. It's infinite. It's infinite spatial value. That means the spatial dimension is infinite. But the temporal dimension, the three-dimensional realm inside it, which is our universe, is finite. But at the same time, since all of this universe is made of matter and energy and they go back and forth hand in hand, technically it's infinitely finite because it transforms. It's in a stage for a finite amount of time. It transforms, boom, it's in that stage for a finite amount of time. And it goes back into another stage for a finite amount of time. That means it's infinitely infinite. And I believe that has something to do with the confusion there. And that's, of course, we know a lot more now than Einstein did back in the day. So, we can figure this stuff out. So space itself is actually the fourth dimension, and the universe is the third dimension. The reason why space itself, technically space is infinite dimensions. Because there's no up and down, there's no right and left, there's no right side up, because down side up is right side up, and right side left is upside down. I mean, there's no right side up in space. So up and down are the same, That means it's got infinite spatial dimensions because of the degrees of freedom. Now, if you look at galaxies, whenever you look at just galaxies, you'll see that they're, right side up, sideways, laying on their side, all this, but they're all right side up, regardless of which way they're positioned. So technically, whenever we put that into measurement, that's a fourth dimensional realm because it has no up or down or left or right. But if you remove this temporal dimension from here, and it's just the spatial dimension, it's infinite dimensions. It has infinite dimensions in it. So, and this right here also represents the cube and the tesseract, which ties in with the 27, with the 27 sectors on a Rubik's Cube and 54 squares, because 6 times 9 is 54. It all ties in. And there's actually, the universe is 200, see, a galactic year is 250 million years. The universe is 54 galactic years old. So, I mean, making it 13.7 billion years pretty much, but the 54 is not arbitrary. That's 6 times 9. The 5 plus 4 is also 9. And it's a circular pattern. The 3, 6, 9, 6, 12, 18. See right here, this is a perfect example, as a matter of fact. 3, 6, 9, 3, 6, 9. So you have your 3, 6, 9, 6, 12, 18, 9, 18, 27. Okay? When you add all these up, you get 18, 36, and 54. You add them all up, you get 108. It's basically squaring the circle. Yin and yang, 6 and 9. And then, of course, you have all this weird stuff. You have 27 constellations in 4 directions. That's 27 times 4. That's 108 again. So just like the hands and the feet aspect, minus the head, of course, you're just your hands and feet, that'd be 108. And just like I was saying with this right here, with the Vitruvian Man and, the pinnacle and all that, and you get the 66. I mean, it's insane. And not to mention the 27, like I was mentioning with the 27, You know what's weird about this? The Rubik's Cube came out 27 years after the Roswell crash. Can you believe that? I mean, it's just like it just doesn't end. It's like everything just coincidentally falls into place. Now, I don't know if they make this stuff happen because, they like to use symbolism, and they do it like this particularly because of the symbolism, or if the universe literally just works with this pattern. Because technically that 27, like I said, that's a lunar orbit. The 6 times 9 is a pion. A pion is 270 times the electron. The muon is 207 times the electron. So it's always a 2 and a 7 there. You're going to get to 18. You're going to get a 27. You're going to get 6s. You're going to get 9s. You're even going to get the 3s because the 3, 6, 9 is not arbitrary. That's your trinity of trinities. Because you have 3, that's a trinity. You have 6, that's 2 trinities. And then you have your 9. That's another trinity. Your 3, 6, 9 is a trinity of trinities. So even Tesla knew some nature of the... Look, man, if Tesla and Einstein got together, man, back in the day and started just putting their brains together, could you imagine the kind of world we'd have now? And if they weren't hindered by the government, if the government let them, come together and think up ideas together, man, could you imagine the stuff they would think up? It'd be insane. But we'd definitely have one heck of a world. I mean, Einstein implementing his physics and stuff, and then Tesla implementing the electronics. I mean, obviously, we didn't know we'd had Wi-Fi, 100 years ago. See, and this is like the singularity. The singularity, it does the same thing that any germ cell. So you have your sperm cell, Y. You have your germ cell, X. Okay, so you have the male nuclear alpha. You have your female electrical beta. So in embryology, the same way, the singularity is going to do the same thing that the embryo does. And it grows in an inverted fashion the same way. Because eventually it's going to transition from leptons. It's going to end up being a nucleonic star. It's like a macroneutron star, completely dense, just like a giant neutron. Because space is something and nothing. Like we was talking about, it's nothing and something. It's 1 and 0, making it completely neutral. So the fabric of space is neutral. It's neutralized. So the first thing that it's going to evolve from that energy is going to be a neutron star. And as it expands, those electrons and protons are getting released from the nucleus of these neutrons, you know. So the nucleonic matter is slowly spitting the particles out as it cools and inflates. And that means it's going to condense to a core. And it's going to invert as the photosphere comes out. Just like you can imagine a supernova, how it collapses and blows up. But instead of collapsing and blowing up, this does a similar thing, but it does it in a slower manner as it's progressing, because it's got to give color charge to all the particles that don't have color charge, like leptons. Because leptons don't have color charge. That's a static realm of the void. That's just the static waters of the universe. It's a static void that's the waters and the sound are going to hue in the light. Okay? And through this process, the singularity is going to end up growing into a supreme fractal being. A plasmatic, hot vein-filled universe. Because, galaxy filaments are basically veins of hot plasma. We live in a mycelial network universe of blood, basically. I mean, you can imagine it like it's a plasma universe. It's plasmatic. Basically, everything's going to condense, and it's going to inflate. So the singularity has its processes, no different than a star, but it works on a quantum level. I'll get to that in a second. Here we go. All right. This would be winter. This is spring, summer, fall. Okay? This is also a left hand, because the universe is left-handed. We live in a left-handed universe. But it's going to recondense and form a right-handed universe. It's going to do this left, right, left, right, left, right for eternity. Okay? And that's the significance of this. Now, not just because it makes sense. All right? So, you have the winter. All of the energy in leptons is going to condense. Okay? You're going to have that static condense into a boson-Stein condensate. Now, typically helium, superfluid helium is pink. Okay? That's going to be the pinky. Okay? So now, from the winter, you're gaining color charge. So it's springing up. Okay? So it's starting to get